Welcome back to our section. On this time, we're going to start the last section, the last unit. And so we're going to start talking about what the universe is, what's out there. And I want you to realize that when we talk about the universe, we are talking about everything that's around here. And so, guys, I want you to remember the universe is a big place, perhaps the biggest. And that's from Kilroy Trout. So if we talk about a galaxy, it's a massive, and I do mean really, really, really massive, guys, gravitationally bound system that consists of stars and stellar remnants, planets, and all that other material that's left over from their formation. We also have then this interstellar medium of gas and dust, and then we have that unknown dark matter and energy that orbits around a common center of mass. And so that's what you've got when we talk about a galaxy. And when I talk about these stars, I mean, we're talking about billions and billions of stars. And so you have a nice, beautiful spiral galaxy right here. You've got the core in the center there, and you've got the spiral arms that come around the outside. This kind of looks like our galaxy, except that our galaxy is a barred spiral. So that means we have a bar of stars coming then through the center, and that's where our spiral arms are coming off. As I said, guys, that's what we'll plan on talking about in the next session. So a typical number of stars in a galaxy, like I said, range from a dwarf galaxy that's less than about 10 million stars to these incredibly giant elliptical galaxies that contain up to 1 trillion stars. I mean, think about that, guys, 1 trillion stars. And as you're going to see when I show you some pictures, especially these pictures of clusters of galaxies, everything on these pictures are a galaxy and not a star. So it says there are more than 125 billion galaxies, and that's just in the observable universe. Because remember, we're only going to be able to see part of the universe. Most galaxies are about 3,300 to about 330,000 light years across, and they are separated by millions of light years. You know, it kind of gives you this kind of feel when you start thinking about how vast space really is out there. And the space in between galaxies is filled with essentially a vacuum, and that's about 1 atom per cubic meter. Some of that best vacuum that you're ever going to be able to get to. Most galaxies we're going to find are found in clusters, just like most stars that we talked about in this last unit were found in clusters. And then those clusters will form clusters and clusters of galaxies, and that's what's called a supercluster. Now, one of the interesting things about the superclusters is they are generally arranged into sheets and filaments that surround these kind of immense voids that we have in the universe. And so that was something that was a little bit surprising when we started looking at really the structure and where all these galaxies were within the universe that we can observe. Here you have just a cluster of galaxies, and most everything in there is a galaxy. A lot of those you see are spirals edge on, then we see these giant ellipticals, and we'll talk about the characteristics of both ellipticals and spirals, as well as these irregular or peculiar galaxies out there. Remember, guys, when you're looking at those, you are looking at a combination of billions and billions of stars that are rotating around a common center of mass. Just another cluster of galaxies. You're seeing a little bit more here. See some nice spirals, some nice ellipticals. It's hard to realize, again, the distances that we're looking at in there. And this picture, you are looking at one of these superclusters, so that essentially everything in there, guys, is a picture of a galaxy and not a picture of a star. So just think about the immense distances that you're looking at in there and the number of stars total that you're looking at in there, if we know that every one of those galaxies are made up of billions of stars. Puts kind of your place in our universe in a whole different perspective, doesn't it? Now, this is that picture I was referring to earlier when you look at plotting all of the galaxies within our observable universe, and you find that they do form these kind of filament-like structures. We will come back to this picture when we talk about the universe itself and cosmology and how did we get all of those galaxies there. Now, in some cases, guys, you're seeing black holes in there. Those are just areas that we don't have photographs of the sky at that point. Those are not really physical voids within space. So how did we decide we weren't the only galaxy out there? Because originally, remember, we thought that the Earth was at the center of not only the solar system, but the universe. And then we discovered, well, That's not true. Our sun is at the center of our solar system, but we only lived in one galaxy, our Milky Way. And so how did we decide that we weren't the only galaxy and there was this whole nother area out there that has all these galaxies that we can see? Well, really, you're going to start back in the early 1900s. And a man by the name of Herbert Curtis observed a nova within the Andromeda Galaxy. Now, at that point, guys, the Andromeda Galaxy was actually considered to be the Andromeda Nebula, and it was certainly assumed to be here within our galaxy itself. It was not recognized that it was truly a galaxy of its own. And in searching those records, going back and looking to see if they could find other those, he found about 11 more novas, and that they were, in looking at them, a lot fainter than the ones that we see here within our galaxy. Well, now something's going on. Either the novas within that particular nebula, for some reason, are always fainter, or that nebula really is much further than what we really thought. And so based on his estimation of distances, he thought that the Andromeda Nebula really was something that was an island universe, something that was not really within our galaxy. It just happened to look like it was. And this is the Andromeda Galaxy. We know now that it is a galaxy full in its own right. It's about twice the size of what we are. It is certainly a spiral, and it's seen somewhat edge-on, and you can see that it has some satellite galaxies going around it as well. Then in 1920, the great debate occurred between Harlow Shapley and Herbert Curtis, because exactly what was the nature of the Milky Way, and more importantly, what did that do to the size of our universe? And it was settled in the early 1920s by Ernest Opek, and it was done by mathematically determining the distance to the Andromeda Galaxy. And then Edwin Hubble came along and photographed it in incredible detail and was able to resolve those outer arms into really individual stars. And so it was really obvious then at that point that we indeed were looking at something that was outside our galaxy. In later years, Hubble, along with Milton Humelson, produced a classification scheme for looking at these galaxies and showed that the universe is expanding, and really started to determine then the expansion rate of our universe. And we still use that equation today, and we are still trying to come in on a really good measurement for the expansion rate of the universe. And that's called the Hubble constant. And here is a picture of Hubble and Humelson. You can see that Humelson is the one on the far left. Then you've got Hubble. And guys, if you are here in Missouri, you know that Hubble was born in Marshfield. Didn't stay here very long, but certainly was born here. And so actually was Harlow Shapley. And he didn't stay very long either. And then if you'll go over 1, 2, 3, 4, 5 people from the left, I think you will recognize Einstein right there. And so really nice historical picture getting all those guys together. Unfortunately, ladies, we're not in there yet. This is the telescope that they used to go ahead and actually make the photograph of then the Andromeda Galaxy. And this is it. And you can see then the writing on there where they were looking at some of the novas as well as then really trying to see exactly what was going on within that galaxy. And I have the Hubble telescope up here, which was obviously named after Hubble, simply because of the contribution that he did make to the study of not only our galaxy, but of the universe in general. Now, we know there are, remember I said they came up with a classification of galaxies. Sometimes, guys, this is called the tuning fork galaxy. But there are 3 distinct classes of galaxies. One of them is called a spiral galaxy, and that's this disc shape with these nice curving arms. Then elliptical galaxies, which are elliptical in shape, but have very, very little dust and almost no arms whatsoever. And then you have the irregular galaxies, and these are kind of just weird galaxies. They look like something has happened to them. They've lost part of their spiral arms. They just have unusual shapes. And we feel like irregulars probably resulted from collisions or disruptions because of the gravitational pull of nearby galaxies. Because we do know that these galaxies move through each other, beside each other, around each other, and when they do that, things within those galaxies change. A lot of times the gas and dust is going to be affected a great deal. Sometimes you're going to have the spiral arms that tend to be pulled out. In some cases, you just completely lose the spirals. And so here's just another small collection of galaxies. And like I said, those galaxies will eventually, if they're on the right path, run into each other. And depending on whether it's a direct hit, one to the side, whatever, will determine what happens as those two go through each other or around each other. Just more pictures of some galaxies. Let me see, these are spiral galaxies. That certainly is an irregular. You can see it just doesn't look like those other galaxies. Something has happened to it. And it was probably destroyed by some kind of collision. So like I said, the classification of galaxies are based on appearances. That's all they're based on is appearance, not characteristics, behavior, any kind of strangeness that's going to show up in the galaxy. It's just if I look at these galaxies, some of them look like this, some of them look like that. So here's our tuning fork, and you'll notice that those irregulars are just kind of off to the side, and they're just irregulars. We don't really have the same kind of classification schemes for the irregular as we do the ellipticals and the spirals. So let's start with a long tail of the Y. You start with E zeros, and we go from E zeros to and it's in a continuum all the way through like an E7, E8, E9. And notice that the higher the number for elliptical, the more flattened they are. It's almost like a cigar shape there. The S0s are very, very round. Think of an S0 as a really big nucleus, with very, very, very tightly wound arms, or maybe even no arms at all. And you can see the S0s are very round, where those ellipticals tend to be a little flattened. And like I said, they get more flattened the higher the E number that we go. And then from the S0s, we go an SA, an SB, or an SC, or an SBA, an SBB, and an SBC. So let's start with the SAs, the SBs, and the SCs. And it really depends upon how tightly wound your spiral arms are, as well as how big that nucleus is. And we'll get into a little bit more of that when we look at the structure of the Milky Way in the next section. SAs have really large nuclei or cores and very tightly wound arms. Where if you look at an SB, it's a little bit smaller core nucleus. Spiral arms aren't wound quite as tightly as what the SA is. And the SC, really small core and kind of far-flung spiral arms. Then if we go down to the SBA, SBB, and SBC, that means with the capital B that there is a bar of stars coming through that core of that nucleus. And so an SBA means that I have a really large nucleus, a really large bar, and that my spiral arms are very tightly wound and they're coming off the end of the bars. Then I have an SBB where it's not quite as large in terms of that nucleus or core. You still got that nice bar, and those arms are not wound as tightly, but they're still certainly wound. And then those SBCs, again, those arms just are kind of outflung. They're not really wound very tightly at all around the core. Our galaxy, the Milky Way, is an SBB. So we do have a bar of stars coming through then the core of our galaxy, and then our spiral arms are coming off the core. And we'll talk about where that bar came from when we talk about the Milky Way itself. Like I said, elliptical galaxies are rated on their, basically how much of an ellipse, from an E0 to about an E7. And then both the largest and the smallest galaxies in the universe are elliptical. We'll have these dwarf ellipticals and then these really large, massive elliptical galaxies. And that's an E0. Now, the other thing, if you look at this, you can say, oh, no, wait a minute, that looks an awful lot like an S0. Well, it does. because this particular E0 is not really very flattened. But the other thing that you find out is that, now not by looking can I really tell the difference between an E0 and S0, but if I look at the makeup of the stars and I look at the characteristics and things like that within that E0, I'm going to find that that galaxy tends to be very old. If it's an elliptical galaxy, it tends to go ahead and have really old stars, does not have a lot of gas and dust, things like that. And that's also another way that you look at in terms of the E0s and S0s. Okay. Now, a lot of times your E0s are not quite so completely perfectly spherical. They will start showing some of that flattenness out of there. Okay. But you can see that just by looking at that, it's kind of hard to tell that those are really old stars, other than the color. And the color is certainly an indication. But more importantly, when we look at the spectrum and we look at what's contained within those stars, we find that they are very different than an S0. There's like an E6. And then we have the characteristics of the ellipticals, little structure and very small amounts of gas and dust. I mean, there's no spiral arms in there or anything else. We find that there's very little or actually no stellar evolution or formation going on with these ellipticals because these are, number one, very old, and because they have little gas and dust. And remember, guys, when we talked about stars, the reason that you have a lot of stellar evolution is because you have a lot of gas and dust. So if that's not there, then I can't have any new stars form. They tend to be dominated by older, more evolved stars, and they're orbiting kind of in a random direction around a common center of mass, where we're going to find out that the spirals are all rotating in the same direction around a common center of mass. And we think they are usually formed from collisions and mergers when we get those really big ones. Okay, and that's the way that these really big ellipticals can become really big ellipticals, is because they either merge smaller ones or because there are collisions, and basically these big ones cannibalize whatever else you have and just get bigger in the process. I mean, look at that really, really, really large one in the center, over there a little bit to the right. Then you have a nice spiral down there at the bottom, and then you can see you have other ellipticals, peculiars, things like that within the picture. But you got a really, really large elliptical sitting there right in the center. And then we have spiral arms, which is what we are. Like I said, they're rated according to how tightly wound their spiral arms are and how large that core, that nucleus is. And we've already gone over that. The A's have a really large core and are tightly wound arms, all the way down to the SCs, which are much smaller core and, very tightly wound, and a lot of times really poorly defined arms. And of course, guys, you're going to get the whole range in all of these. And then, as we talked, you can have that bar of stars in across there. That's an SA. Now, you can almost look at this and see some of that gas and dust, where when we looked at that elliptical, boy, you didn't see any gas and dust on that thing at all. There's an SB. Now, we're going to come back to this and looking at those types of spiral arms right there and why they are so spread out and so wide, as opposed to some of these other galaxies that I'm going to show you that kind of have these really nice, very well defined. But the reason this is not an SC is because those spiral arms still are relatively tightly wound. You can certainly see they're not as tightly wound as an A, but they are certainly better wound than what a C is. Every place you see those pink areas, that's where you're getting areas of active stellar evolution. Now there's a nice SBC. You can see it's got a bar of stars coming through there, and those spiral arms are coming off there. So spiral arm structures with lots of gas and dust, hence you're going to have lots of stellar formation going on, lots of open clusters, dominated by young stars because you do have so much stellar evolution going on. And we find that, within the core is where you're going to have those older, kind of more evolved stars. And remember, guys, we're all rotating then around a common center of mass. So how are we going to get spiral arms in a galaxy? Well, we think there's probably two leading hypotheses for why you have spiral arms in a galaxy. Number one might be density waves, and the other one are shock waves. Now remember, guys, shock waves within the interstellar medium certainly accounted for why we had stellar formation. Okay, well, that also may be because those are shock waves, those are pressure waves that are moving through there. That could also cause then a bunching of these stars. Here's a nice galaxy. You can see lots and lots and lots of stellar evolution going on in those arms. So where did those arms come from? So a density wave is simply a density permutation that's going to move along at a different speed from the speed of the objects within it. So in other words, it's moving differently. It's moving independently. And the spiral pattern of the arm is a density wave that rotates more slowly than the galaxy's stars and gas and dust. And guys, on Blackboard, I have a little bit more that's going to help you kind of understand this, and I've laid it out a little bit better on how that goes ahead and forms. And I've got some URLs that kind of show how these density waves form. And the spiral arm is not actual material. You know, we see it there because the stars in there is actually condensed up, and so what we're seeing is the spiral arms that are there because of the condensation of stars. We are not seeing then the actual density wave itself. We are seeing the result of that density wave. And like I said, the gravity wave is moving independently of the star. Now, I've tried, yeah, I know this is not stars, guys, but we are looking at cars going around a circle. And so you're going to kind of look at the same thing. I want you to watch the cars, and then I want you to watch how the cars then start kind of condensing together. And so you're kind of having a bunching of these cars there, and then that kind of looks like it moves through there. Well, that's kind of, not exactly, but kind of what's going on. You get a bunching of a density wave, so that means all the stars in that area where that density wave is kind of bunch together, and then you go ahead and get that separation. So you get the bunching again, and that bunching is again where those stars are being compressed and going ahead then and kind of showing up as an arm itself, as opposed to just an area in there where you have an equal distribution of stars. There are, again, some more URLs on Blackboard to kind of show you exactly what I mean by that a little bit more. So also, in addition, when we talk about that gas and dust getting compressed, then, guys, we've talked about before, that's when you're going to have stellar evolution. And so they tend to show up within those arms because that's where you're getting that compression to go ahead and start that evolution of stars again, or that formation of stars. And this is just a nice one. Look at all that pink area within those spiral arms. And that's what you have then for new stars. And you can see that there's this thing sitting at the end of one of those arms, and that's probably formed from a collision, something like that, that happened years ago. So as the density of the arm increases, that increased gravitation is felt by the gas and dust. And as we've talked, that's going to trigger then the collapse of the clouds, which is going to start more stellar formation. And so the arms basically are appearing to travel through the stars as the stars orbit in their path. And so where that arm is traveling through, you're getting a bunching of stars. And so, like I said, we see the effect of what's going on with that spiral arm. Also, shock waves tend to follow the same format as density waves. And so we think that also could be part of an issue, is looking at what happens with those shock waves that are traveling through the galaxy, which cause the stars basically to be bunched up. Large spirals are thought to have formed from density waves radiating outward from the core, and that's causing then bunching near the core. And bars are found in about 67% of all spirals, so we don't think it's anything unusual. Okay, just a natural formation of what happens as the density of these waves that move through the galaxy show up. Now, there are three types or flavors of spiral arms. And you can see they're the grand design, which is about 10% of the galaxies out there, of the spiral galaxies, obviously, guys. And there you have really well-defined arms. Then you have a lot of multi-arms, which is kind of what we are. And there's about 60%. And then you have these incredible spirals that you know that there's arms there, but they're really not well-defined, and they're kind of spread out. And you get these what are called flocculent spirals that actually turn out to be, I think, one of the prettier types of galaxies out there, if you can talk about nice and pretty galaxies, but very impressive galaxies with these big arms that are out there. And that's obviously kind of a well-defined. That's kind of like one of these which are multi-arms. So you have just areas where those arms have gone ahead and split off a little bit, or you've had spurs of their galaxy arms that have formed. And then, like I had said, you have these really incredible flocculent spirals where you can see that there's definitely arms there, and you can see some of that gas and dust, but, they're not really well defined. Okay, but they are still certainly spirals, and there still is stellar evolution going on in them at the same time. I just think they look really impressive. So now let's look at comparisons of these stars, or these galaxies. In terms of ellipticals, notice you're getting from about 10 to the 5th solar masses to about 10 to the 13th. So you get really small, really large. Diameter is about 3,000 to about 600,000 light years. Population of stars in an elliptical galaxy is very old. And interstellar matter, like I said, guys, essentially no gas and dust, which means we're not going to have any little baby stars that are going to form. So if we look at spirals, on the other hand, they're someplace between 10 to the 9th and 10 to the 12th, so they're kind of in that middle range. Notice they're not as large, nor are they as small. So they're 15 to about 150,000 light years. They have both old and young, with the young stars being in the arms, the old stars being within the core. And they do have lots of gas and dust. And then irregulars, 10 to the 8th through 10 to the 11th, so again, they're kind of in the middle there. Any place between about 3,000 to about 30,000 light years. They have both old and young. Well, if they have young, then there's got to be some gas and dust in there. Usually there's lots of gas. It kind of depends on the dust. Kind of depends on how that irregular got to be an irregular galaxy, and exactly what happened to it in the past. Did it run into something? Exactly what happened to it. And when we get talking about clusters of galaxies, things like that, we'll come back again to how those irregulars might have been formed. So let's talk about something called stellar population. There are generally two categories of stars found in any galaxy. There's a population 1 and population 2. Population 2 stars are really old stars. And we kind of talked about that when we talked about our sun. It's a third generation star. So that means it's part of that population 1 star. We find these population 2 stars are found within the globular clusters. They're found within the core of our galaxy. They are by far the most prominent stars in an elliptical galaxy. So this is an old globular cluster. Actually, guys, I'm wrong. That's not a globular cluster. That is actually a small elliptical dwarf galaxy. Sorry about that. That's not quite what I thought. Yeah, that's one of those little dwarf ellipticals. And then population 1 stars are younger. They contain more heavier elements. And, as I said, guys, for our purposes, heavier elements are anything beyond helium. Usually found in the disk and the arms of the spiral galaxies. Stars in the bulge are also population 1 stars, because of the fact that you had that really massive first generation of stars. So if you think about what's in our core, those population 2 stars, which are really the old ones, and they've already gone through a lot of their stellar evolution. And when we talk about all the black holes and things like that that were formed in the core of our galaxies, they are formed from those population 2 stars. Well, if we have a lot of population 1 stars in throughout the galaxy, especially through those spiral arms, that means as these stars then go off, we've got a much richer mixture, basically, of heavier elements then within a galaxy. And that's another thing when you look at the difference between galaxies. We find spirals have more of those richer type of elements, the ones that are heavier than helium, because you've had all these stars that have gone off. You still have stellar evolution. They're going off again, producing even more. And so we get then more of that material within those spirals. Another picture of the spirals going up, and notice that really hot gas and dust right there in the center. Well, that's what happens when you have galaxies that go through each other, and you have material that's left over that can then go ahead and undergo more evolution, more stellar formation. And then we find out that black holes seem to be found in galaxies of these really larger galaxies found in the center. And that's true about our galaxy, guys. You look toward Sagittarius, you're looking toward the center of our galaxy, and we know that there's lots of black holes. And when we talk about the Milky Way next time, we're going to look at what's in the center of our galaxy. And we obviously cannot see it with visible light, but we can look at it with radio waves and with X-rays and things like that. And we get a whole different version of what the core of our galaxy looks like. Now, we also have things called dark matter and dark energy. Not exactly sure what's going on, but dark matter seems to, according to current hypothesis, seems to account for almost 90% of the material in the galaxy. Now, let me say that again, guys. Dark matter, which is matter that we can't see, seems to account for about 90% of the material within a galaxy. So that means that all that galaxy, when we look at it, that visible part is only about 10% of what we really consider to be the galaxy. So now the question is, if we can't see it, why do we think that it's there? Well, it's because as we started looking at these galaxies, we find out that the rotational speed of these stars at the edge of the galaxies is not falling off the way we expected it to. Okay, it makes sense that if I have a galaxy, then the center of mass is going to be more toward the center of that galaxy. And as I get further and further out from the center of that galaxy, my gravitational attraction then seems to go down. And so galaxies at the furthest edge, stars at the furthest edge of our galaxy should be rotating around their center of mass slower. But that's not really what we see. You see that I've got a predicted. Well, it looks at your velocity, and your velocity then falls off with distance. But that's not what we observe. We observe that velocity staying up there. Well, then something's got to account for why that velocity is as high as what it is. And if we think it has to do with gravitational attraction, then something's going on. Is it gravitational attraction? Could it be something that has to do with the fact that there's a repulsion effect, and everything seems to be getting forced away from a point, which is causing that velocity to even be faster? Guys, we're not exactly sure what's going on with that dark matter and dark energy. Now, this is a cluster of galaxies, and so everything in there, essentially, with the exception of a couple of things that have spikes on them, things that have spikes on them are stars, but otherwise, everything that you're seeing out there is a galaxy. And this is artificially colored for that blue, and that blue is what we think is the dark matter. So you're looking at the mass that we can see, and again, that's about 10%, and that blue color then accounts for 90% of the mass, which could account then for why we see these speeds at the very edges of the galaxy. They're not falling off the way we expect them to. Well, one of the sections that we will do together is we're going to look at CERN and look at what's happening at CERN, which is the big accelerator, trying to determine what's going on with dark matter and dark energy, things like that. hopefully within another 5 or 10 years, we'll have that nailed down pretty quickly. It's not there yet, guys. We still don't know what's going on. But we will talk about some of the experimentation that's going on to help determine what's going on within the dark matter and dark energy. So what I want to do is finish here today, and then when we come back, the next section, I want to go ahead and look specifically at the Milky Way and what it is. Well, we know it's a spiral galaxy, but let's talk then about the general characteristics of the Milky Way. So with that, guys, I'll see you next time.